When we're talking about kinetics in chemistry, we're talking about how fast a reaction occurs. If we consider just a simple reaction, for example, A turns into B, the reaction rate, which is the change in concentration per unit of time, would be rate equals the change of concentration of A per unit of time. Since the concentration of A at the end would be lower than its initial concentration, and because we want the rate to be positive, we have to put a negative here. And if we want this in terms of the products, we don't need to put the negative because it's gonna be positive. When we're talking about kinetics, we also deal with the rate laws. So the rate laws with in kinetics looks like this. Here's the rate that we have just described before. Here is the rate constant, and this indicates the order of the reaction, which can be either 0, 1, or 2. So these right here are the rate laws, and here's are the integrated rate laws, integrated with calculus. So what we need to understand here is that I can plot the graph of the concentration of A, versus time. And it's important to understand how the graph looks like. All of them can be referred to the equation y equals mx plus b, which is the slope of a line, which is the equation of a line. So here, the negative k is the m, the time is x, and these right here are on the white interceptions, and this is y. It's important to understand the factors that influence our reaction rate. So one of these is the orientation of the molecules. If the molecules are not well orientated, they will not collide successfully. For example, if I clap my hands right like this, I'm not gonna have like a clap. So they have to be well orientated. Another thing is the energy of activation, and this can be achieved with the right number of speed. So if, for example, if I clap my hands right like this with not enough velocity, I don't clap my hands successfully. So they have to be with a minimum amount of speed. As far as a reaction goes, we can also plot the potential energy versus the time. So the two graphs looks like this, and right here is the energy of activation, which is the difference between the peak of the graph and the initial potential energy. And right here is the delta enthalpy, which is the difference in potential energy. Because here the difference in enthalpy is negative, this reaction is exothermic, and because right here the delta enthalpy is positive, the reaction is endothermic. When we have a reaction, it's not just that step, but it's a sum of multiple elementary steps. So here's our two steps of an overall reaction that we can figure out. So I have to add all the reactants and all the products and see what cancel. So the chlorine cancel and this cancel too. So This is the overall reaction, and it's important to understand also what a catalyst is and an intermediate. So an intermediate, it's a molecule that it's used up in the steps and it doesn't take part in the actual in the overall reaction, and it cancels in one of the steps. Then a catalyst is an enzyme that speeds up the reaction and lowers the activation energy. But it's not used up, it's recycled, and it appears at the end. So here the chlorine is the actual catalyst because it appears at the end. So it's used up and then it comes out again. Instead, ClO, it doesn't take part in the reaction. So kinetics has to do also with equilibrium. The definition of equilibrium in chemistry is when in a reaction the rate of the forward reaction is equal to the rate of the backward reaction. So the rate of the backward reaction would be this, while the rate of the forward reaction would be this. Then if I divide them, because those are equal, because of the definition of equilibrium, they cancel, K cancel, and if I replace the ratio with Kc, I get the equilibrium expressions. So this is a sample problem, and the first question is to find the rate law. So I go ahead and I try to figure out which experiment they have the same concentration so that they cancel when I divide them. So I'm going to choose number 1 and number 3 because I see that the concentration of B is the same. So I write 6.3 times 10 to the negative 3. Then the K, the concentration of A to some power, and then the concentration of B to some power. Then I divide it by the other rate law, so as I see here, this cancel, the rate constant is the same. So I go ahead and plug it in the calculator. I got 9 here, and this seems like 3 to the x. So x has to be equals to 2. Now I have to find the other exponent for b, so I go ahead and find which cancel. So I'm gonna choose number 2 and number 3. The concentration of A to some power that I figured out it was 2. So these cancel. Then I plug it in the calculator. So here I got 4, and this seems like 4 to the y, so y has to be equal to 1. So the rate is equal to K times the concentration of A to the second times the concentration of B to the first.